Alright, hello on the Virginia 5, and I thought today would be a nice day to just do a little walkthrough of the ship's engine room and talk about our steam engine and how everything works. So, looking in through this open hatch, you can see our boiler. So this is the top of it, where all of the steam comes out and is sent to various systems on the ship. We always draw steam out of the very top of the boiler to try and avoid getting a bunch of water in it. So these are the main lines which run to the engine and to all the other systems on the ship, as well as up to the steam whistles, which is very important. So back here we have our engine room. Yes, it is a nice open engine room, easy for everyone to see. The engine room has always been open like this. It's not been walled in. It was considered a bit of an attraction on these mosquito fleet boats for passengers to be able to come down to the engine room. It would also just be ungodly hot in here if it was all enclosed. See, our engine room is blessed with all of these windows which we can open in the summer so our engineers don't die. But first we have up here our boiler. So this is a modern boiler. This is a Babcock & Wilcox water tube boiler built in 2001. This up here is what we call the steam drum. So this is actually where the steam builds. It is usually about halfway full of water, so there's room on top for steam to build and build pressure. Boiler's empty right now because we're doing maintenance. I'll cut in a few clips of the inside of the drums, which are pretty cool. You can see all the water tubes that make this a water tube boiler. And up here we have our pressure gauge. We operate at about 180 psi on this ship with a maximum pressure of 220. And then, because this is a modern boiler, it does have a control panel. So this contains all of the automatic shutoffs and automatic fuel and air feed and all that kind of stuff. The Virginia 5 here does meet all modern Coast Guard safety standards for carrying passengers, and that means some concessions have to be made in terms of historical accuracy. But it's better for us to keep the ship running even if we have a little computer here that helps run the boiler. We do also have manual controls for pretty much everything as well, because the computer is not always right. So back here you'll see these two bells. These are engine order bells. They're no longer in use, but these are original to the ship. So the captain has no control over the engine on the Virginia 5. If he wants to change the speed of the ship, he has to signal down to the engineers. This is how we used to do it. We have the gong and the jingle, and different patterns of gong and jingle indicated different speeds to the engineers. We have a little key on how the gong and jingle system worked, which I will put up on the screen. In the modern day, instead of using a gong and jingle, we do use an engine order telegraph, which we have right here. So we have a bit of an unusual telegraph. The Virginia 5 is a passenger ferry, so she really doesn't have any business doing flanking speed. This telegraph is a piece of naval surplus, so it came off of a Navy ship. It was installed on the Virginia 5 in 1969. So currently, above it we have a little key. Each speed on the telegraph has been assigned in RPM. So when the captain calls down for, say, standard speed, the engineers know to change to 90 RPM, which is usually around 7 knots. Then we have 3 options for going backwards. We can track the speed using the tachometer. So changing the speed of the ship is done here in the throttle. This valve is pretty simple. More steam that goes into the engine, the faster the engine goes. So you just open this for more speed, shut it for less speed. And then we do also have reverse. This is a direct driving engine, so there's no transmission. In order to reverse the ship, we have to actually reverse the valve timing of the engine. There's also no clutch, so there's no neutral. If the engine's moving, the propeller is spinning. So for reverse, this is our reversing lever, or Johnson bar. And if the captain calls down for astern propulsion, usually the engineer will shut the throttle to stop the engine, or at least slow it down, and then take the lever and throw it. and we'll look below so you can see what the valves do when I throw this. Can you do it one more time?
Sure.
Just like to have lots of clips for this. So that's what we call a Stevenson linkage, and it reverses the valve timing of this engine, and that makes the ship's crankshaft start spinning in the opposite direction. We do not need to stop the engine to do this, but we usually do because our steam engine's 121 years old. And going from full head to full astern is a lot of stress on the propeller shaft, as you might imagine. So we will talk a little bit about this engine and how it works. This is what we call a triple expansion steam engine, and that is a type of compound engine. That means that the steam goes into one cylinder, and then that exhaust is what drives the next cylinder. So there's only one in and one out from the engine. So steam comes in through the inlet and through the throttle, and then it goes to the high pressure cylinder. In the high pressure cylinder, the steam expands, which pushes the piston down. That same steam is then sent through the valves here to the intermediate pressure cylinder for a second expansion. So the intermediate pressure cylinder is larger than the high pressure. As steam loses its pressure, the surface area of the piston increases. So each piston produces the same force on the crankshaft. And then from the intermediate pressure cylinder, the steam passes through our low pressure valve here and expands in the low pressure cylinder, which is of course the largest on the engine because it's operating at the lowest pressure. Steam enters the engine at about 180 psi, and then by the time it gets down here to the LP, it has about the same pressure as an unopened soda can. And then the steam leaves the engine, and we turn it back into water and pump it back into the boiler. We are now in the lower engine room on the Virginia 5. First thing you see here at the bottom of the ladder are these two pumps. These are both duplex steam pumps. These are the feed water pumps, and their job is to pump water into the boiler. We have two of them. We only use one at a time. Everything in the lower engine room has a backup in case something fails while underway. So we have our inboard and outboard feed water pumps. Alright, so we're turning over here to look back at the boiler, and this is the firebox. So this is actually where the fire is burning in the boiler. At the bottom is the other drum, which we call the mud drum. So the mud drum and the steam drum all the way at the top are connected by hundreds of tubes which wrap around the firebox. That's why it's called a water tube boiler. Alright, so this is the inside of the firebox. Both sides are all of the water tubes, which is what makes this a water tube boiler. Other side is where the burner goes. So, pretty roomy.
Does the
usually
burner do one or two passes?
Just one. But you can imagine this is usually just a giant ball of flame in here. Yeah, pretty cool. This increases the surface area for heating. So water tube boilers tend to heat water into steam faster and more efficiently than fire tube boilers, but they also take up a lot more space. So this here is where our burner rods go. This is an oil burning steamship, and she always has been. Originally the Virginia 5 burned bunker oil. We converted to burn diesel number 2 with the installation of this boiler in 2001. So the way this works is we have an array of burner rods here. Each burner rod is different. They differ on the amount of fuel they allow to flow through them. The more fuel that goes into the firebox, the hotter the fire is, and the faster we make steam. But that can also limit how long we can run slowly, because we don't have a good way of venting off excess steam. So generally before a cruise, The captain and the chief engineer will discuss what kind of speeds they want to make that day and choose the appropriate burner for that range. So once a burner is picked, it then is picked up and we slide it into the boiler and then run diesel through it, and the diesel is lit on fire. So we have two lines coming into the burner. We have fuel, and then this is steam. We have what's called a steam atomizer. So we take pressurized steam and inject it into the burner. The pressure of that steam atomizes the diesel into an extremely fine spray, and that allows us to get an almost complete burn out of our fuel. If you see the Virginia 5 well underway, you may notice that there is very little smoke coming from our smokestack, unless something's wrong. This may disappoint steam fans to not see big clouds of smoke coming out of the smokestack, but it pleases the EPA, so. It also means that we are getting, of course, more energy out of our fuel, which is also good for money. So turning away from the boiler, we come over here to the crankshaft. Now this triple expansion engine has a stroke of about 1.5 feet, and it has a top speed of 200 RPM. It is rated for 400 horsepower, but the real advantage in steam is the amount of torque it produces. Steam does not have a torque curve the way that an internal combustion engine does. It instead produces equal torque at all RPM. This engine produces around 30,000 foot-pounds of torque, which is why we do not need a transmission. So we have our high pressure piston rod here, our crank rod up to the crosshead, up to the piston rod. The crosshead here runs up and down on this guide, which we call a crosshead guide. These circles etched into it just help oil flow down the length of the guide to keep this lubricated. We also have shaft lubricators on all of our shaft bearings. So these are the valve gear. You can see how a Stephenson linkage works. There are two eccentric rods on the valve gear. One eccentric rod is for going forwards. This eccentric rod is for going backwards. So when I threw the big reversing lever up above, it just shifts over the valve rods, putting the reversing valve rod into action. Steam engines like this are double action. That means there's both a power downstroke on the piston and a power upstroke. The valves control which end of the cylinder is the intake end, the top or the bottom. By reversing the valve timing, a piston that was getting pushed up instead gets pushed down, and that reverses the rotational direction. Fairly simple system. Our intermediate pressure crank and piston rod, and then our low pressure crank and piston rod down at the end. The pistons on this engine are 120 degrees offset from each other. There's 3 of them, so 120 degrees times 3 makes 360. That means that this is a balanced crankshaft. It does not need a flywheel or counterbalances, which is nice. Over here we have the oil can collection on the ship. So our oilers do an oil round every 30 minutes, and different oilers have different preferred oil cans, so we just have a selection. We have a few crew members who like to just scour antique stores for vintage oil cans, because we do break them. And then this red pump here is the fire pump. This pumps water to the ship's fire hoses. We have 5 fire hoses on this ship for firefighting purposes, probably on board the ship. This is a wooden boat, so fire is a pretty big concern. So this is another duplex steam pump. The way these work is that they have a steam end and a water end. As the pistons on the steam end go back and forth, they pump water up out of the through hole and then out through the lines. And then this one just goes directly to the ship's fire main. So, aft of it we have another pump which is basically identical. This is what we call the general service pump, and it is hooked up to this big manifold here. And this pump actually has the ability to take the place of any other pump on the ship. So if something goes wrong with the fire pump, this can become our new fire pump. If something goes wrong with the feed water pumps, if something goes wrong with a circulating pump, this can step in and do that job by lining it up via the manifold it's connected to. So here at the aft end of the engine, this is our jacking gear. It's engaged right now. This is used for rotating the crankshaft by hand when we're doing maintenance. So the worm gear here engages to this big gear here, and then a ratcheting handle fits on top, and a crew member gets to stand down here and ratchet furiously until we can turn the crankshaft around for whatever maintenance we're doing. And then this big box just behind the crankshaft is the ship's thrust bearing. So this is our thrust bearing. It's what I call a horse collar type thrust bearing. The purpose of this is to absorb the thrust that the propeller produces and transfer it to the ship's hull. So you can imagine that as a propeller pushes the ship, it does mean it has to push against something. So we don't want the propeller pushing against the crankshaft because it'll shove the crankshaft out of alignment. We have to transfer that push into the hull, and that is what the thrust bearing does. So as the propeller is pushing the ship, these compress, and then they are bolted into the hull of the ship. So then the force of the propeller pushing is transferred to the hull of the ship. When we go into reverse and the propeller pulls instead, these also still push upon each other and still transfer that force to the hull. The fiber you see in here is horsehair. Horsehair acts like a sponge, absorbing oil, and also acts like a wick. It helps feed oil down into the bearings. And then once we leave the thrust bearing, we have the propeller shaft. So this runs all the way out through the back of the boat, through what's called a stuffing box. Alright, so back here we have our stuffing box, or packing gland. And this is what prevents water from coming into the ship around the propeller shaft. The other thing back here are the ship's water tanks, potable water, and reserve feed water for the boiler. Our hot well over here heats water before it goes into the boiler, because we don't want to put cold water into the boiler. You can also see one of the ship's modern generators back here. But over here we have another steam pump. This is a little vertical single cylinder steam pump. This is our circulating pump. So if we look up over here, we have the ship's condenser off in the corner. The condenser is where the exhaust steam from the engine is cooled back into water. So the cooling power for the condenser comes from raw water, so seawater or lake water outside. That's what the circulating pump does. So this giant impeller here draws water from outside through this valve, sends it around the condenser, and then gets pumped overboard again through the big valve over there. So it does not mix with the steam or condensate going into the boiler. So it just sits back here, pumps away, doing its thing, spinning this big impeller. Then we have two more pumps over here. We call these the air pump and the vacuum pump. They look very different, but they both do the same thing. These are actually condensate pumps. They take the condensate coming out of the condenser and send it to the feed water heater or the hot well to get preheated. The condenser, because it turns steam into water. Now when water turns into steam, it expands. When steam turns into water, it contracts, producing a vacuum. That's also why we sometimes call this the vacuum pump. By pumping the water out of the condenser, it helps increase the vacuum the condenser is producing, and that actually improves the efficiency of the low pressure piston, because it means that one side of the piston actually has a vacuum on it, while the other side of the piston has the pressure on it. Alright, now, pretty big piece of machinery. Very impressive. This engine is about 90% original parts and has been removed from the ship once to be gone over. Steam engines like this run at very low RPM, and there's no combustion happening inside of them. That means that the wear and tear is fairly low over time compared to an internal combustion engine. That means with the proper care and feeding, these engines can last a very long time. It was pretty common, even in the olden days, for a steam engine to outlast the hull that it was installed in. So there's plenty of steamships out there that received used engines from previous ships, which of course is what happened here. The Virginia 5 receiving the used engine out of the Virginia 4. So we're back here in the upper engine room. One of the things we have over here is the ship's instrument panel. So we have 5 different gauges here. So the engine, of course, has 3 cylinders, and each one operates at a different pressure. so each cylinder has its own pressure gauge. I'm gonna go over and get a closer look at this. So we have the high pressure gauge, the intermediate pressure gauge, and the low pressure gauge for each piston. See that the LP piston gauge does have actually a vacuum, because that piston sometimes does operate at a vacuum on one side. Then this is the vacuum pressure for the whole system going into the condenser. And this is what we call back pressure. So I will explain what the back pressure is as we go around to the other side of this gauge. So back here we have our feed water heater. The feed water heater here heats the feed water before it goes into the boiler, because we do not want to put cold water in a hot boiler. So the way that the feed water heater works is that we have cold water coming out of the condenser up into here, and then we have all of the little steam pumps down below. Their exhaust lines also go into the feed water heater, which is what this big pipe is. So as exhaust steam from the pumps goes into the feed water heater, it heats the cold water, and it also condenses the steam. So it is a heat exchanger with two functions: heating feed water as well as condensing steam. So the back pressure is tracking the pressure of the steam that's going into the feed water heater. If there is not enough cold water going into the feed water heater to condense all of the steam that's being fed into it, we have a relief valve that will blow that off right up here. We try to avoid blowing the pressure valve, because the Virginia 5 is a passenger ship, and that tends to startle passengers when this whole area suddenly just fills with steam. So we have a handle here on the top of the engine, this long one, and that will actually dump excess steam going into the feed water heater down into the condenser instead. So an engineer usually is trying to keep an eye on the back pressure, because if it gets too high, you need to come over here and open this handle to dump the excess steam, or the pressure relief valve will go off. So that is the basics of the engine room on the Virginia 5. We have our jacking gear engaged sign. This is to remind people to not try to start the engine if the jacking gear is engaged, because it will break it. And then the last little thing we have is over here. You'll see another steam pump. This is the ship's old generator. So this is a single cylinder steam engine. Got the flywheel on the end. The flywheel is not for a belt. This is not belt driven. Flywheels just even the stroke of these big thumping single cylinder engines. So the steam piston in here, back in the day, would spin this dynamo with the brushes and the magnets to produce electricity, and then this provided all of the ship's electrical power. It is no longer hooked up, you may observe. That is because the ship has far greater electrical needs in the modern day than she did in 1922. This generator is nowhere near powerful enough to power a single wedding DJ, much less all the nav equipment we now are required to carry on the Virginia 5. So it has been disconnected. We have modern diesel generators to provide our power instead, but it is still here because, one, it's an interesting historical display, and two, the ship would probably list really hard if we took it out. Alright, so take one last look at the engine. I'll throw some video of all of this stuff running right at the end of this video so you can see what this all looks like in motion. And if you have any questions about our engine, or about steam engines, or marine engines, feel free to leave them in the comments. Thank you for watching.